Let's now learn how to classify charge stability diagrams with neural networks. So, you saw in the previous parts of this module that you can get a beautiful charge stability diagram like this one. But before you get there, before you see all the transitions clearly in both dots, you need to tune the plunger gate voltages into the regimes where the transitions in both dots are visible. And just a few years ago, this has been still a manual task. But in the end, we have a measurement data that look kind of like an image. So it could be a natural question to ask whether an AI can do the task for you. So what we specifically want to do is to measure as little as possible. The charge stability diagram on a previous slide had a beautiful, perfect resolution with a lot of points and all transitions visible. But if you are in a tuning part of your protocol, you don't want to sit there and measure this perfect charge stability diagram for every voltage configuration that you try. So you want to measure as little as possible, take a very rough scan of your charge stability diagram, and then classify whether you are in a 1-dot regime or whether you are in a 2-dot regime. Now, for this pre-generated charge stability diagrams, you see that just looking at it, it's very quickly to say 1-dot, 1-dot, 2-dot, 1-dot, 1-dot, 2-dot, and so on. What happens in practice is that you will have a bunch of noise on top of your measurements, so actually the transitions will be less clear. For the purposes of this lecture, we prepared a data set where the transitions are still recognizable, so you don't have to train super huge neural network, and you can just do this task with a small one, but I will show you some real experimental data in the end. So, would you remember from setting up a neural network reading part of this module is that a very simple neural network classification task is that of having images from two different classes, Star Wars and Star Trek in this case, and build a neural network that is able to tell whether each new picture is a character from the class A or a class B. This is just a binary classification, and you hopefully read how to build a neural network that achieves this task. If this does not look familiar, click a few times back and go review the neural network primer section once more. With that in mind, it will not be surprising if I replace my Star Wars and Star Trek characters with different type of charge stability diagrams. One will be double dot charge stability diagrams instead of Star Trek, for example, and single dot charge stability diagrams for a Star Wars, for example. So that way, I have images just like I had before, and I have a binary classification. Am I in a 1-dot regime, single dot charge stability diagram, or am I in a 2-dot regime, double dot charge stability diagram? So in that sense, everything can stay the same, it's just a binary cross entropy. Loss function is just a two-class classification problem of a labeled dataset. So it's not super hard to imagine that this is perfectly transferable from the image learning to the different kind of image learning, where our new type of image are your charge stability diagram. What we prepared for you is a data set like this, where you have a lot of different generated charge stability diagrams that one comes with the label 1 for 2-dot and 0 for 1-dot. Arash is going to walk you through a coding demo where you are going to do exactly this thing. In the first part of your exercise, you are going to build your own neural network in PyTorch. The example we have for you is really minimal. You have your input images, 50 times 50 pixels. Then you have a 16 neurons in the intermediate layer, and then you have just the two outcomes, probability dot 1, probability of dot 2. And that's really it. And then you can train a neural network model that will reach some accuracy. It's not super accurate, but it's pretty decent. If we want to improve, we are going to do what you saw in a neural network primer reading, and that's replace the dense network with a convolutional network. Again, this is an image analysis, and we are looking for a specific type of feature, namely which ways the lines go. So you can build this with just a slightly more difficult neural network where you will have some finite number of filters that you will then feed into the linear layer and again into the two outputs. You see on the example here that Arash will show you when you run the code together, that now the accuracy for training and testing is much higher. So for this case, convolutional neural network is a probably much nicer idea. So in your coding demo, you are going to first see how to do it and then fill in both your feed-forward and convolutional neural networks. And we invite you to experiment with the numbers of neurons, layers, filters, kernel size, any hyperparameters you want to experiment with, and try to reach the maximum accuracy possible in minimum amount of training steps. And that will be your exercise. Let me finish this part up with some real-life experimental applications. Since 2019, basically, there has been a lot of applications of what we have seen in this module. This is example from 2020, Darulova et al. You see that examples here of single and double dot regimes are slightly less nice than this data that we generated for you from a simple theoretical model, because in practice you have, of course, way more physical phenomena coming into play. But the beautiful thing is that in that paper, they just did pretty much what we did in this module on a much simpler example. There has been a lot of different applications since then, but all of them carry the spirit of what we did here. Treat your charge stability diagram as an image, label it with the feature of what you want to look for in the data, and just train a supervised feed-forward neural network to do that decision for you. This is super nice because when your experimental parameters change a little bit, if your neural network is trained robustly enough, it will generalize to a new different noise scenario and find good voltages anyways. So nowadays, this is something that is super routinely embedded into the different experimental setups in many leading labs around the world. And it's also something that has already reached the speed of experienced human tuners. So while so far this has been successfully applied to smaller devices only, this is something that is becoming more and more a norm in the field, and it's something that you probably want to embed into your tuning workflow instead of doing it by hand. With that, we arrived at the end of this module, and I'm looking forward to see you in module 2.